Hi, I'm Matt, and in this video we're going to go over exothermic and endothermic energy diagrams, also known as exothermic and endothermic energy profiles. So first we're going to look at the exothermic energy profile. So you'll realize that on our x-axis we have the reaction coordinate. That's just a fancy term for how far into the reaction we are, almost like time. And on the y-axis we have the potential energy, measured in joules. So one of the distinctive features of all energy profiles are that they have the peak in the middle where we go up and then come back down. As we start to label this diagram, we'll start to realize why that happens. And then since this is exothermic, we're releasing energy, so the final energy is lower than the initial energy. So now let's start labeling our energy profiles. At this time, I would suggest you sketch one similar to the one I have on the screen, so you can label it as we go. You'll realize I drew dotted lines at the top of the peak, where we start, and where we end, just so when we draw arrows, you could see exactly what we're pointing to. So the first thing that we're going to discuss is this line A. That is the potential energy of the reactant. And you can see that because that's where our line starts and touches the y-axis. The second thing we're going to label is that line B. B is the potential energy of the products. This is where we end and the final energy left over after the reaction. Next, we're going to label the line C. This is the activated complex or transition state. You can see this goes all the way from the x-axis all the way to the highest peak in the graph. This is the maximum amount of energy in our reaction at any point. This is where our reaction actually occurs because this is after the upward sloping part or the activation energy has been added. As stated on the last slide, to get to that activated complex or transition state, we have to add energy. We call that energy the activation energy. So line D here is the activation energy of the forward reaction. It's important that we mark that's the forward direction, because this reaction could happen in reverse, and then it would follow the same exact path, but backwards. We would start over by the line B and follow the path until point A. So if this reaction was occurring in the reverse direction, the activation energy would be E, because that's the amount of energy needed to be added to get us to that peak, to our transition state. Now the last thing we want to label on this energy profile before changing it up a little is our heat of reaction, represented by line F. The heat of reaction is the total change of energy in the system as we go from start to finish. So here we could see that we end up with less energy in the end, which is why it's exothermic. So the heat of reaction here, represented by line F, would be negative, and can be found by taking the heat of the products, or line B, minus the heat of the reactants, line A. So the last thing we have to discuss when it comes to an exothermic energy profile is what will happen if we add a catalyst. Now the first important thing to mention with the addition of a catalyst is that the heat of our products, or the energy of our products, doesn't change, and the heat of our reactants doesn't change. So our starts and endpoints don't change. It's only what's in the middle that changes. And you can see that change is that the peak would be lower, because a catalyst lowers the activation energy, so the peak is less steep since the activation energy is lower for the reaction. Since the catalyst lowers the activation energy for a reaction, we'll see that it lowers the amount of energy in the activated complex of the catalyzed reaction, because it absorbed less energy for the reaction to occur in the first place. So the last two things we're going to label on this diagram are the activation energy of the forward catalyzed reaction and the activation energy of the reverse catalyzed reaction. You'll see here how once again the activation energy of the forward reaction is the line that goes between the beginning of the reaction, or the potential energy of our reactant, and goes to that peak of the activated complex, represented by that small line H. And you could see how that's much smaller than the line we had earlier for the non-catalyzed reaction. And the catalyst works in both directions, so our catalyzed energy of the reverse reaction represented by I will also be smaller than it was in the non-catalyzed reaction. Now we're going to shift on to endothermic energy profiles. So here you'll see how it looks very similar to the exothermic with one main difference. You'll realize that here we start at a lower energy state, and at the end we have more potential energy, because an endothermic reaction absorbs energy from its surroundings. Now we're going to label the endothermic energy profile. Since it's very similar to the exothermic energy profile, we're going to go through it a little faster this time. So just like in the exothermic, that first line from where we intersect with the y-axis down to the x-axis, represented by A, is the potential energy of our reactants. And the final part of our line where it levels off down to the x-axis, represented by B, is going to be the potential energy of our products. Once again, our activated complex is going to be our highest point on the graph, represented by C, and it's the distance between that high peak and the x-axis. Now, our activation energies are going to be in the same places, but they're a tad different from the exothermic reaction. Here, you'll see that on the left, where we have D, which is the activation energy of the forward reaction, and then on the right we have E, which is the activation energy of the reverse reaction. You'll realize how, since this is an endothermic reaction, the activation energy of the forward reaction is much higher than that of the reverse reaction, as seen by how D is longer than E. The other main difference we see is in the heat of reaction. In an exothermic reaction, we saw that the heat of reaction was negative. In an endothermic reaction, the heat of reaction is going to be positive because we're moving from the height A to height B. The graph is higher, so it has a higher value. And if we did products minus reactants, we would get a positive number. Now let's look at a catalyzed endothermic reaction. We'll see how, just like the exothermic, we still start and end at the same values. The only difference is that the peak in the middle is lower. Since that peak is lowered, everything that corresponds to that peak is lower as well, such as the activated complex. The activated complex is less energetic because that line G is shorter, because less energy was put in for the reaction to occur in the first place. As previously stated, the activation energy decreases due to the addition of the catalyst, so that we're going to use that line H to represent this, which is much shorter than the line we had earlier. And as also stated earlier, a catalyst works in both directions, so that line I is going to be shorter as well. Now that we've looked at both energy profiles, let's look at some of the questions we might ask. You'll realize that this is a graph similar to we saw earlier, but this time there's numbers on it. And the question is this exothermic or endothermic, and what is the heat of reaction? So the first thing we should notice is that we start at a high point and end at a low point. This means that energy was released or lost in the reaction to the surroundings, meaning this would be an exothermic reaction. Now that we've concluded it's an exothermic reaction, we could find the heat of reaction. And if you remember, the heat of reaction is equal to the heat of the products minus the heat of the reactants, or the line on which we end minus the line on which we start. So we end at 20 joules, and we start at 50 joules. So we would do 20 joules minus 50 joules to give us that our heat of reaction is negative 30 joules. Now, using that same graph, I have one more question that I would like to go over, and that's, what is the activation energy of the forward reaction? So remember how the activation energy of the forward reaction is the difference between where we start to that activated complex, or that top peak. So the first thing I always like to do on one of these questions is actually draw in the arrow that represents what we're looking for. So you'll see I drew the green arrow on the graph between the 100 joule line and the 50 joule line. So all we have to do to find the activation energy is do 100 joules minus 50 joules, which gives us that the activation energy of the forward reaction here would be 50 joules. Now that we've tried a question together, I encourage you to pause the video and try these 5 questions on your own. All 5 of them pertain to the graph on the right. So what type of reaction is this? Use the correct term to label line A, B, and C. What is the potential energy of the reactants? What is the potential energy of their products? That is not one of the three labeled lines. And then, what is the numerical value of the heat of reaction? That line is also not labeled. The solutions will be provided for you on the next slide. So the solutions are as follows. This is an endothermic graph. Line A is the potential energy of the reactants. Line B is the activated complex or transition state. Line C is the activation energy of the reverse reaction. And then for question 3, the answer was 10 joules. For question 4, it was 50 joules. And then for question 5, it was 40 joules. Hopefully you got these. If not, feel free to leave a comment with any questions below the video, and I will get back to you as soon as possible. Thank you so much for watching. Have a great day.